Now, if somebody comes to you and tells you that every cat is black, and you say, all right, prove that to me, and then carry a black cat come show you, does that prove to you that every cat is black? No. No, similarly, if someone were to tell you to prove that the limit of a function, someone were to tell you that to prove to them that the limit of a function as x approaches a is equal to L, you can't just pick out some biased values for x and say that these values are approaching x from the left and they're approaching x from the right, and their corresponding f of x values are approaching f of a, and so that implies that the limit of f of x as x approaches a is equal to L. No. So how exactly is it that we carry out that requirement to prove that the limit of a function actually exists? We do that by a number of methods. And let's look at three of those methods. We have the first one that we call direct substitution. And all this method is saying is that if we're finding the limit of f of x as x approaches a, all we need to do is plug x equal a into the function and we get f of a. Let's look at a simple example. Let's look at the limit of 1 over x plus 2 as x approaches 2. This direct substitution method is saying all I need to do is plug 2 everywhere I see x. And what do we get here? We get 1 over 4, or 0.25. So by direct substitution method, what this is saying is that the limit of 1 over x plus 2 as x approaches 2 is a quarter. Now, another method that we use is called the factorizing method. And what this does is that it says, all right, if a factor of the numerator is in the denominator, then we can use that to our advantage. And many times we use this method because the direct substitution method would just not work, or it would just not give us a true answer as to what the limit is. So in our case now, we want to find the limit of x squared minus 4 over x minus 2 as x approaches 2. Now, if we were to plug in 2 into this function, as the direct substitution method suggests that we do, we would end up with 2 squared minus 4 over 2 minus 2, which would give us 0 over 0. And the fact is, people, we do not want that. So we need to get rid of that. Why? Because we cannot divide by 0. This would be implying to us that the limit does not exist. But before we can come to the conclusion that a limit does not exist, we need to carry out a more rigor. We need to carry out this method with more rigor. So what do? We say, all right, let's simplify the numerator, or let's factorize rather the numerator. So we have that this is the limit of x squared minus 4. That's a difference of 2 squares. So we have x plus 2, x minus 2 over x minus 2 as x approaches 2. Now, that cancels that. So that leaves us with what? That leaves us with merely the limit of x plus 2 as x approaches 2. And now, after we have factorized, we can do what? Direct substitution. So what do we get? We get that this is the limit of 2 plus 2 as x approaches 2, which gives us 4. In other words, the limit of x squared minus 4 all over x minus 2 as x approaches 2 is equal to 4. Now, let's look at our final method. When you were doing module 1, you heard the term conjugate. Now, let me remind you what this makes reference to. If we have a radical function square root of x plus the square root of y, then the conjugate of that function is the square root of x minus the square root of y. Now, when we're finding the limit of radical functions, we are going to exploit this relationship, the relationship that exists between a radical function and its conjugate. Let me show you exactly what I mean. Let's say that we are supposed to find the limit of the square root of x plus 8 minus 3 all over x minus 1 as x approaches 1. Now, if I were to use direct substitution, I would end up with a 0 in the denominator, which is exactly what I do not want, because that would be implying that the limit does not exist. So I say, okay, let's multiply this function by 1. So I have the square root of x plus 8 minus 3 over x minus 1. I'm going to be multiplying that by 1. And so let's write 1 in a different form. Let's write it as the square root of x plus 8 plus 3. Notice the difference here. This is a minus, this is a plus. All over the square root of x plus 8 plus 3. So notice that that is still 1 because the two terms that we're multiplying by cancel. Now, let's simplify this a bit. So now, notice here that we have this function here. We have this numerator here, and we have this numerator here. So we have a plus sign here and a minus sign here. So what that implies is that we're going to be looking here at the difference of two squares. So we're going to be left with x plus 8 minus 9 all over x minus 1 times the square root of x plus 8 plus 3 as x approaches 1. Now, upon simplifying further, we come to see that this is the limit of x minus 1 all over x minus 1 times the square root of x plus 8 plus 3 as x approaches 1. Now, this cancels with that, leaving us merely with the limit of the square root of x plus 8 plus 3 as x approaches 1. And this is where we can now do direct substitution. Because upon doing the direct substitution, that x is equal to 1, we would merely be left with the limit of this function here being equal to just 1 over 6. In other words, the limit of the square root of x plus 8 minus 3 all over x minus 1 is 1 over 6 as x approaches 1. So all in all, what we're seeing here is that when we're required to find the limit of a function, the first thing that we'd want to do is direct substitution. But there are times when direct substitution gives us the false impression that the limit of the function does not exist. So what do? We carry out methods that have a bit more rigor than direct substitution, including factorizing and using the conjugate when it's a radical function. So these methods will enable us to find the limit of the function if it really does exist.